Have you ever seen the 1996 film Twister? With the announcements about the upcoming sequel film and my own delays on getting another script for October written out and filmed, I thought it was a good time to use the script I had written months ago. Seriously, the majority of the script was written long before the first October video was even a thought, and I just had a lot of setbacks in filming it. So anyways, I'm going to try to answer some questions that popped in my head about the film, like, what all did they get right and wrong in terms of the science and historical parallels? What is the current state of study for tornadoes? Did anyone ever do what they did in the films? And what is the suck zone? And does it feel... We'll skip that one. In doing research for this, I found it hard to stay focused on the scientific inaccuracies and accuracies of the film, mostly because I got distracted by two stories that easily parallel it in some places and heavily deviate from it in others. But with a little creative liberty, I'm sure we can stitch together a story that easily answers all the questions that I had. Now, before we get into those stories, I feel it best to state that tornadoes are violent and destructive weather phenomenon. This will become apparent as we go on this journey, but this is here just in case you weren't already aware of it. May 9th, 1993. It's Mother's Day in the quiet town of Wiley, Texas. People are out and about making purchases for family get-togethers, buying gifts, and generally enjoying the day surrounded by family. A young boy, roughly 2 years old, is at home waiting for the rest of their family to show up for the day's celebration. At the southern edge of the city, just past its border into the neighboring city of Saxe, a tornado formed at noon and started moving to the northeast. The first place it would hit is the tiny Glen Knoll trailer park, full of mobile homes that were largely unprepared for a tornado, and the home of the young boy. The tornado's path took it to the north, directly striking the local hospital, then through a pharmacy, neighborhoods, and eventually to the lake just north of the city, where it damaged boats at a marina before it dissipated. It had traveled 12 miles from start to finish. Fortunately for the young boy, it had missed his home and spared his family, although they did have to cancel the rest of the day's planned events. The same amount of fortune cannot be stated for the rest of the city, as the tornado had left 63 injured with one fatality in the same trailer park that it had struck first. According to the family of the young boy in the story, their first warning about the tornado was seeing one of their neighbors' sheds spinning in their yard. To quote the movie Twister, "We had no warning." Warning sirens didn't go off until after the tornado had already made it to the main part of the city. Official assessments in the coming days would rate it as an F2 tornado, which, while destructive and terrifying in its own rights, could have been much worse for a stronger tornado given where it first impacted and the route that it took to the city. In total, there were 16 tornadoes recorded on that day, with this one being the strongest. For those of you who have seen the movie Twister recently or just happen to have a better memory than most, you can see some of the parallels I'm trying to draw to the opening of the movie. Family with a small child caught up in a tornado. And while it wasn't the same rating and the boy didn't lose any of his family, the events can be seen as similar. What can't be said as similar is the path he would take moving forward in comparison to the characters of the movie. Whereas Joe in the movie went on to chase tornadoes, the young boy in our story went on to make this YouTube video. The earliest memory that I have is the glass of our home breaking as this tornado tore through our neighborhood, but not much more than that. So I had to get the rest of the information from family, TV reports at the time, and the slim data issued by our national services. And let me tell you that those last two were harder to find than I would have liked. This should give a relatively good idea for the state of tornadoes and their warning in the early 90s, as well as the reporting for them after the fact. Large storms were easier to see, and so it had an easier time to predict if they would produce tornadoes or not. Warnings and alerts weren't typically issued until after the tornado was confirmed to have formed and had already started its path of destruction. Funnily enough, this last bit is still true to this day for the local sirens. It's usually up to a city to sound them, and most places won't until they're already confirmed, which makes it too late for those in the initial path. I do suppose now would be a good time to actually explain the rating system for tornadoes before we get too far ahead of ourselves. I'll attempt to do this as simply and quickly as possible, as most of the information here is readily available online, and I do recommend going and looking it up for yourself since it's insightful and makes for an interesting story on its own. The Fujita scale was developed in 1971 by Ted Fujita and ranks tornadoes on a scale of F0 to F5 based on estimated wind speeds inferred by the damage dealt by the tornado. Getting accurate data for tornadoes is relatively difficult and dangerous, as one can imagine, so when trying to figure out just how strong one is, the only reliable source of data that can be looked at is the damage path. In the early 2000s, the United States decommissioned the Fujita scale in favor of the enhanced Fujita scale, which had been developed to account for more accurate assessments of the damage done by a tornado. In general, the wind speeds needed to deal the damage they were finding was lower than what the Fujita scale had established. The new scale categorizes from EFU to EF5, with the low end being unknown or unidentifiable, with no defined damage, and the high end being only described as incredible damage. And since we're being sidetracked to explain some science, let's go down the rabbit hole a little bit. In the course of doing my research for this project, I was led to an extremely interesting endeavor in the 1980s. The Ottober Tornado Observatory, or TOTO, project was an attempt to gain scientific measurements from within a tornado. The probes were large and bulky, requiring at least 2 people to deploy. The scientists would have to unstrap the probe, place it in the path of an approaching tornado, and then quickly evacuate the vicinity. If we take a good look at what these probes look like, they should have a remarkable familiarity to something else you may have seen. Perhaps something from a movie? That's right, people. The movie Twister is based off of this project right here. Unlike the movie, however, the TOTO project was never successful. The probe had too high a center of gravity for extreme wind speeds, and even the weakest of tornadoes would knock it over. But where it was bad at its actual job, it was quite useful as a portable weather station for non-tornadic storms. Ultimately, the project was retired in 1987 due to safety and logistical concerns. I think I need to move on from this. June 24th, 2003, near the city of Manchester, South Dakota, an engineer had just finished placing several probes in the path of an approaching F4 tornado, with just over a minute before it would tear through where he was standing. On this day, Tim Samaras would capture the largest drop in atmospheric pressure ever recorded. His probes, the hardened in situ tornado pressure recorders, were commonly referred to as the Turtle, were aerodynamic cones containing an array of sensors to capture pressure and temperature, as well as other measurements at ground level. After this groundbreaking event, Samaras would have the notoriety and backing to form his field research team. The Tactical Weather Instrumented Sampling in Tornadoes Experiment, or TWISTEX, was funded in large part by the National Geographic Society. And if you've ever seen a show by Nat Geo documenting tornadoes, then there's a good chance that it was Tim and his team that either got the footage or were the stars of the show. They were even one of the storm chasing teams for the last 3 seasons of Discovery Channel's Storm Chasers. The work of Tim Samaras cannot be overstated in the world of meteorology for tornadoes. Much of the data he collected has been used to improve forecasting models and increase the warning times for tornadoes. While what he did was dangerous and could easily be seen as reckless, it was done in the name of saving lives. If you haven't been paying attention to this story so far, this is the real-life version of Bill from the movie Twister. Unfortunately, we don't live in movies, and tragedy is never far behind a tornado. May 31st, 2013. 8.3 miles west-southwest of El Reno, Oklahoma, at 6:03 p.m. A monster of a tornado touchdown. Typically, when you think of a tornado, you imagine one spinning vortex, and that's the tornado. This is a potentially deadly assumption for most people to make. While there may be a visible vortex, there's a high likelihood that the tornado is much larger than what you can see. In some cases, you end up seeing multiple vortexes within the tornado, which cause a lot of people to assume that there's more than one tornado on the ground. El Reno's tornado was much like this, a multiple vortex tornado. But looking at the footage for it, there is clearly something different from most of the other multiple vortex tornadoes. The vortexes weren't at or near the center of rotation, but rather the edges. The clearest of footage from that day shows it off quite well, and it's almost as if the vortexes are circling each other in a macabre dance, never stepping into the center. This tornado was massive. As it tracked along its 16.2-mile path, it would take out the local airport. As it crossed US 81, it did something unexpected, even for all the seasoned storm chasers and meteorologists observing the storm. It expanded to an area of 2.6 miles in width, making it the widest known tornado ever recorded. At 6:28 p.m., as the tornado continued to move towards the east and into the more densely populated areas of Canadian County, an anticyclonic satellite tornado formed to the southeast of the primary tornado. This isn't an uncommon thing to occur, and as its name implies, an anticyclonic tornado spins in the opposite direction of the primary tornado in the storm. At 6:42, the primary tornado tracked over Interstate 40, and at 6:43 had dissipated. For 40 minutes, the storm tracked through Oklahoma from the city of El Reno and ending just outside of Oklahoma City, causing an estimated $35 to $40 million in damages, injuring 151 people and claiming the lives of 8 people. 3 of them were the TwistX team of Tim Samaras, his son Paul Samaras, and their colleague Carl Young. Because the tornado didn't enter into any major population centers and formed in a largely rural area, there wasn't enough damages to classify it any higher than an EF3, although the wind speeds that were recorded from it were in excess of 290 miles per hour and potentially reaching above 300 miles per hour. Those wind speeds alone are in the highest estimation for an EF5 based on damage assessments. I'm sure you can start to see one of the glaring issues that we have with how we classify tornadoes. With the advent of new technologies and Doppler radar, such as high-powered mobile radars, we can easily get accurate measurements of wind speeds for a tornado. This is something that would have been deemed as impossible in the early 90s, as the only way to do so would have been through something like the Toto probes or even one of the probes that Samaras had deployed. When the enhanced Fujita scale was adopted, this wasn't a technology readily available, and so it still relies on estimated wind speeds based on visible damage a tornado produces. At the time of the El Reno tornado, that same technology was being implemented on stationary radars with nearly the same degree of accuracy. It's potential that if we use the measurements we can observe through radars, that we could categorize a tornado during the storm itself and give better warnings to those in the potential line of devastation. That may be hopeful thinking on my part, though, but at the very least, giving those readings higher weight when categorizing a tornado would help us to refine our methods and see what the potential range of damage can be expected out of them. But I'm just going on a tangent here. In the years since 2013, there have been a number of new technologies on the market that are being implemented to better research tornadoes. Drones and small rockets are being equipped with instrument packages so they can be flown through the center of tornadoes to take all the readings that we haven't been able to safely get in the past. And deploying them is far easier and safer than the probes that had been used up till this point. The legacy of Tim Samaras is the new methodologies being utilized after he proved that you could do it in the first place. Well, hey, thanks for watching the video. I hope you enjoyed it. I know that it's a deviation from October, as you know, it's a whole month, but I ran out of time to try to get another script done. So, yeah. But the information here is super interesting, and honestly, if you have the time, go and look it up for yourselves. The stories are great. There's a number of biographies done about Tim Samaras and the work he did. It's really, really riveting stuff. If you enjoyed the content, I hope you like, comment, subscribe, do all that stuff. It really does help me out in the long run. And hopefully I'll be back next week with the final video for October. Till then.